Okay, folks. How's everyone feeling?
Wait for spring break.
All right, two more fluid classes and then we're done with this week. So we're gonna do vorticity now. There's a new homework that I'm gonna post today. I think just do it this week and over the break. On the topic of homework, I'm assigning questions from the book, which means there's the possibility that you can find the solutions online. Or you're working with someone and they can explain the whole problem to you. What I'm seeing as a recurring problem with students is that they are writing down the right answer, but have no idea how they got there. Okay? I don't care. I'm not losing because of that, right? I'm not paying money. I'm not wasting my own time. You may think to yourself, well, at least I got it done. And that's perfectly fine. Maybe that's your educational goal. But this is an upper division elective. You're not required to be here, right? So I would strongly encourage you, if you are doing something like that or similar, just stop, think about what the impact to your learning is, because you'll finish the homework and still not know how to do it. In which case, you haven't done the homework. You know what I'm saying? And it's clear to me who is doing this, because I can see how you're writing. And I'm like, this is exactly correct, but you can't tell me why it's correct. Right? As opposed to, if you struggle, if you come and you ask me questions, if you make one mistake, I'll know that it's your work, because you're not supposed to get it the first try. These are not easy problems. It's supposed to be hard, so you struggle on them and you get better and you become a better physicist. The real world does not involve someone giving you the answers. The answers will almost never be present. And it's your job to figure them out. Okay, rant over. Today, lecture 8-1. Here's what the new homework's gonna look like. I hope this comes up. One more computing problem. A couple more from chapter 4, and then we'll go into vorticity. You know you need two homeworks. Huh? Yeah. Why? To catch you up. Come on, you gotta work. How much time are you spending outside of class? I don't think there's only 3 Dodger games all week from break. That's all 3 that you can go to. Good. So that leaves you Thursday, Friday, Saturday, Sunday, and the Saturday and Sunday before. Hold on, let me count. That's 6 days to do one. You can do one problem every 2 days. For the Lord. Those are for the Lord. You're right, there's 2 Lord days. Okay, so let's do 4 days. 4 days, 4 problems. Okay. All right. No, the idea here is that you get better at doing fluids by doing fluids. And in particular, how many folks are reading the book before they start the class? Okay, good. How many people think about looking at the outside of the book? A skimming. That's the right way to start, right? You don't need to read it like it's the Bible, which means that you leave it in a book or in a drawer and never open it. You don't need to read it like it's your brother's diary, okay? So keep notes on it and post it on Tumblr, okay? You need to read it, you need to skim it, so that the time you see it in class, you'll understand it for a second time. And it's perfectly okay, especially if you have the digital version, keeping it open while class is going on, so you can like write notes in it is great. But don't do all of your thinking in the book, right? Allow yourself a little bit of space to kind of be like, wait, do I understand this? Without looking at the book for immediate answers. Does that make sense? Okay, folks, that's money to the ceiling. Oops, let's do this one. We're gonna go really fast today. Really, really fast, okay? So who wants to be the first victim? Alphabetical?
Are we all taking care of one section or like entire equation?
Entire equation. All right, Dan, you're first.
Shorted. And that's telling us that the pressure and
The top one?
yeah, the top one.
Top one doesn't have pressure in it.
Or the density. my
Yeah.
bad. So the density over time and the density as it moves throughout the space is 0. So that's telling us that it's being conserved, and that's the whole that's the mass in the system.
Good. Okay, so let's break that down just so we can do it faster. How would I read the first line again?
Density over time, but the
No, you're still reading it. You're still reading it. So
Okay.
just consolidate what you said, one line.
Okay, so the conservation of mass that we see up there. Oh, just like that.
That's it.
Okay.
Conservation of mass.
Gotcha.
If you want to elaborate, right, that's the first line. Second line is, to your point, there's a steady and an vector term. And there's no ways to generate mass. Right, that's what it says in English. Good. You can also say, if you want, that the total big deep derivative of rho is 0. That'd be the third way to say it. Okay. Elliot, you next.
The bottom equation is the conservation of the Planck tensor,
Good.
which basically means it involves the pressure forces, the body forces, the stresses. It has the incompressibility term afterwards.
Good,
And the
that's it.
rest is just
Perfect. See how quick that was? So first line, conservation of mass. Every term. Good. And then if you needed to, if you wanted to go one layer deeper, how would you go?
one layer deeper after describing each of the.
Yeah, so you've described all the different terms, right? You might be able to say something like, okay, this conservation of momentum, which is here on the left, or on the left, due to all of these sources and sinks. And you could say, if you want to go like a little bit more specific, you could say for an incompressible fluid, this term is 0. For an immiscible fluid, one that doesn't have any viscosity, immiscible, a non-viscous fluid. These two terms are 0. And those would be the simplification, right? So for example, if we're thinking about Bernoulli's equation uses an inviscid fluid, one that doesn't have viscosity, and it's just these 3 terms in concert with one another. These 3 mix it up a little bit. Okay, ready? Who's up next? Okay. Yeah, we got the short end of the stick here. But that's okay, only 3 people have to go today, and then on Wednesday I'll get the other 3 minutes. We'll do reverse alphabetical order.
That's the conservation of energy.
Good?
On the left, the E is internal. I'm sorry,
That was right.
internal, and the other one is, it's not, kinetic is not the right word, I don't think.
This is the right word, yeah.
Okay.
So this is the internal and kinetic energy.
The first one is body forces,
Good?
like work done by gravity.
Yep.
The second one is PDV work.
Good?
Viscous heating is the third one.
Good?
Kinetic energy done by pressure.
Good.
And then I think that one is the stress and strain tensor.
Correct?
And then the last one is work done by heat.
Good. So this is all like 99.9, right? The only thing that I would say is pressure gradient. But everything's perfect, right? And that's how quickly you can read it off. And as we get to see them more and more, we're going to internalize them, right? So again, top level, that is conservation of energy. The second level, you go through, you're able to talk about all the forces. Some modifications, of course, G might be electromagnetism in some cases. For the general part of this class, it won't be. It's only be gravity. That's why we use G. We say here, this is the stress tensor, but it's the derivatives of the stress tensor. So this is coming from shearing, right? So this is definitely right. This is viscous heating, and this is shearing work. Done. Look how fast that was. 7 minutes, record time. Okay. So we talked about the Bernoulli equation. We talked about these sheets of constant B. You remember those? You're gonna have something like streamlines. Streamlines follow the flow, and you have vortex lines. Something maybe we're not super familiar with, but we're gonna sort of get a lot more clarity when we talk about vorticity dynamics. And then these sheets of constant B, those are the locations where you can apply Bernoulli's law, right? In the forms that we saw before. Okay. When you do any differential equation, you need a boundary condition. In particular, when we're thinking about how we're going to solve fluid dynamics, whether we're doing that analytically, or if we're doing that on a computer, you create an array. Because you cannot simulate all of space on a computer, right? Is that right? There's a little caveat. You can do all of space, but you have to take infinity and turn them into. So for example, one thing that's really interesting is as long as the force goes to 0 at infinity, like 1 over r or 1 over r squared or something like that, you can remap the xy plane so that stuff can go to infinity. You can map it onto what's called a conformal grid that you can represent all of space in a box. It's stupid, but you will see that if you get to like general relativity. Okay. So this is the part that matters. And this is where we're going to spend a lot of time thinking about boundary cases. Anything that's in contact with the fluid, if it's touching the fluid, the molecules touching the surface, they're not moving. So naturally, we can't have some discontinuity in the flow. It can't go from a large value, positive value, to immediately 0. Because the first thing that we see with diffusion is that it likes to take anything that's sharp, a sharp discontinuity, and flatten it out. That was the thing we showed on the computer, right? You start with this nice big wave, and the wave sort of gradually fans out. So you could imagine some fake situation in which you quickly move a rock, and all of the flow around the rock, right, all of the individual particles, they're initially 0. And the rest of the water, maybe it's 0 too. You move the whole rock, but then you have some propagation of that effect because the fluid is in contact with one another, they're all bouncing into each other. So then you create vertical velocity gradients starting at 0 and going out. And we'll talk about boundary layer conditions in the mathematics behind this. But when doing it on a computer, you have to just map to the boundary properly, right? Yeah.
So that fluid is flowing. So if I'm thinking as an example, like if I have water flowing like here on the desk, the molecule that's touching the desk, the velocity of that water molecule is 0.
Yeah.
But everything above it is not 0.
Yeah.
That's crazy.
Yeah, it's really crazy. So that's the weird thing, right? Is you say to yourself, okay, 0. How far is it basically there? Right? Because 0 is kind of like a wishy-washy idea. Of course, nothing is really not moving. Atoms and molecules, they have a little bit of jitter from the fact that they're subatomic particles, or is that they're atomic particles, right? They respond to quantum mechanics, but we're looking at them on a broad scale. So what we have to do is we have to go smoothly to 0. So for example, something like sine, right, starts at 0 and moves up to a value that's real, or not real, larger than 0. Cool. Okay. So what's this word again? I said it earlier, but I said it wrong.
Invisible.
Yeah. What does it mean? So no viscosity invisible. That's very slow, but you get the idea. Immiscibles. Yes. Immiscible, immixable. That's not really where it comes from, but that's kind of the idea, right? No mixing. Give an example of two immiscible fluids that you use pretty regularly. Very good. Oil and water. Give me two examples of immiscible fluids that you use in your kitchen. Okay, you have homework this week. What? Yes, oil and vinegar. So, to really draw your true Italian heritage, Matteo Prismani, right? What you gotta do is over spring break, you get what's called a baguette. Okay, this looks like bread, but it's long and it tastes really good, not like shitty bread, okay? You get fresh. You go to bakery, you get fresh bread. You go home, you take a dish. It's a fluid dynamics problem. Take two dishes, actually, you're gonna do it twice. In one, you're gonna pour oil, then you're gonna pour balsamic vinegar, and you're gonna put a little salt, maybe some pepper, whatever you want. And then you dip the bread into the dish. And tell me what the bread tastes like. Okay, and then the other one, okay, you put both of them in there and you mix them, and then you tell me what that is. Actually, we're gonna get oil, it's gonna suck. Good. So sometimes what folks will do, right, is they'll have two dishes, one with the oil, vinegar, and one with the oil, and then you dip it in. And you're like, well, you shouldn't mix them. Well, they're not gonna mix anyway, because they're immiscible. Immiscibility does not have to do with density, does not have to do with the viscosity. This is just a different property of the fluid. They don't like to mix because the types of molecules that are in there, they're just not interested. Right? What happens to water when you put cinnamon on it? What?
The water will go.
Yeah, it's hydrophilic, right? So the particular things that are trapped in your water solution, right? Because of course the base of vinegar is water and the base of oil is water as well, right? The things that are mixed into that solution, I will give it its properties. Okay. Happy? Healthy? Okay, so if you have a fluid that's in contact with another immiscible fluid, it means they're not mixing. Can you give me an example of one of these that you see when you go, say, spring break, going down to the beach? It's not one that you can ingest at the same time. Well, you can kind of ingest this.
Sunscreen.
What's two? I need two.
Okay.
Okay, this one is really, really weird. It's gonna need you to take a step back. You can sort of think of this when you're laying on the beach. Okay, you're looking at the beach. What are you looking at? What? Water, ocean. What causes the waves?
Out the wind.
The wind. The wind is a fluid made of air. Those are immiscible fluids. Right? So they sit on top of each other, one not permeating the other. So when I say fluid, I mean fluid. Not the phase of matter, not liquid, fluid. Does it have fluid properties? And in fact, they do have fluid properties. And of course, you can get into a little fight with me. Well, you know, if I open my mouth and I drink the water and eat the air at the same time, you're right. Okay, then you can mix them. And of course, if you churn it up, you can froth it up, but they'll separate out and the air will come back out. So if you have them in contact with one another, you can conserve mass. This is going to give you boundary conditions. This tells you how much of this fluid you started with and how much you need to end up with. Similarly, you can conserve momentum, but you have to think about the ways in which these two fluids interact with each other. So does the wind give the water momentum through shearing forces? So you need to define them, right? That's what this would be, the surface tension forces, the surface shearing forces. And of course, you can conserve energy just by thinking about the ways in which they interact. Sure. I think we said this last time, right? Talked about how we're going to do this problem for computational. the computational fluid flow. So you need to solve the Poisson equation. Just so that we're clear what's happening here. Do you remember what the Poisson equation is? Yeah, del squared, let's call it phi equals,
Either zero or zero. 'Cause the
Yeah,
other one is
good.
positive.
yeah, let's call it gobbledygook. Okay, so del squared equals some gobbledygook, right? And if you look at the equation that we started with, this conservation of momentum one. We go back here. So remember that this really is ddt, and there's some spatial derivatives. And on the right-hand side, only spatial derivatives. So the technique that we use when solving computational fluids is to first separate things from time equals space. Now remember, this is not math, this is me talking about algorithms. So on the left-hand side, you have some derivative with respect to time, d rho dt or du dt, however you want to talk about it, right? And you put the spatial derivatives on the other side. Now, in order to solve the spatial derivatives, you need to use Laplacian. So essentially what this is saying is that this is this. Right? How do you advance the simulation? How do you make it go forward in time? No one loves integrating. Anyone who says they love integrating is an alien.
Oh. That's the bigger range.
Nope. We're going to remember doing this on a computer. We got to bring it forward in time. Forward time centered space is the technique that we use for the homework. This is the centering space one. We talk about how to break apart those spatial derivatives, right? Forward time requires us to use one of three methods essentially that you've learned. Euler's, RK2, RK4 are all valid. And these basically do the following. The value phi at some new time, I'm going to call it phi prime, is equal to phi plus a little step, right? H times the derivative phi. And another way we can say this is x at some new time equals x plus the velocity of x this time. Right? That's Euler's equation. Now this thing here, d phi dt, that is blob. So once you solve this left-hand side and you figure out what it is, you just plug it in here for blob, multiply it by h, and step the integration forward by one step. Oop. To do that, of course, we will need, you need to think about how to solve things in the 2D. So if you're in computational, you are feeling really on top of that right now, because we just learned how to do things like the relaxation method or over relaxation, where we solve something that looks like a Poisson equation. We try to solve it. We update it, we update it, update it until we get that value correct. And then we just use the output of that to set it forward. Right? So this takes a long time for a fluid. Because however long it takes for you to update this component is only one time step. So if you want to run a fluid for 100 years, it's going to take you a really long time. You have to think about it, you have to take very small time steps to see the flow. This is why fluids are very hard to do. It's also why, you ever wonder why you can't get the weather accurate more than like 2 or 3 days out? Yeah, so fluid load's changing, that's certainly true. We can talk about chaos a little bit later, but generally speaking, these are just hard to do. So you don't just run one simulation. So for example, when you ever look at a hurricane, they say, here's the path that it's gonna take. That's the most likely path. But they run the simulation hundreds of times and they model each of the different paths that it can go, and then they create a little cone of uncertainty. And that cone of uncertainty broadens the farther out you get from the date of the simulation. Because there's so many things that can happen along the way that you're not accounting for in these large simulations. But all of those simulations, this is what they do. Solve space, update time. Solve space, update time. Solve space, update time. Okay. Okay. Cool, that's it. Watch it. Class. Let's think about Vorticity. What is Vorticity? Go across. What do we mean? Yeah, conceptually, it has to do with rotation of the fluid. Is the rotation in the fluid, etc. I mean, so if I said del cross U is 0, you would say zero rotation. Yeah. What would be like a hand wavy way of saying this, like your cousin is?
Upward spin.
Sure, spinny, rotationally, yeah. I might add something like how twisty, how curly. These are all good adjectives. Spin, rotation, twist, curl. This is the right idea. You're thinking about this motion, right? That's what you're looking for with vorticity. Good. So vorticity, when you have some arbitrary flow, is not necessarily unidirectional. So let's say you have some example. Give me an example of a flow that is rotating.
Water drain.
A water drain. Good. All right, this is a really fun one. Let's try it. Let's look from above. Let's imagine that the sink's hole here is at the origin. How does the flow go? We want it to move the direction. Yeah, it's going like this. Okay. And wait, did I draw these wrong already? Is it going faster or slower towards the hole? Faster for the center. Okay. So in fact, it does something like this, right? And maybe far away, you don't even notice them. Right? Okay, so is there vorticity there?
We go all the way around.
Well, let's assume that I mean, it's a drain, right? Let's think about this. Del cross U. What is del again? Yeah, so this is asking how is it changing with space crossed into each component? In this case on the left, we're thinking about, you can do it in XY, but that's probably going to hurt our brains. Let's think about it in the context of R and theta. So there is U theta and UR. What's the UR here? According to the lines that I just drew, nothing is going in the sink. Now, of course, that's not properly correct, because there's a little bit in order for the stuff to actually drain out, right? So I could maybe draw that more like a spiral. Like this. So each one goes in, but I'm not gonna complicate it like that. Let's do the first part, so we said UR is 0, what about U theta? That's right, it's non-zero. That's all I want, non-zero. Okay, so we're looking at the terms that are 0 and then terms that are non-zero. Okay, is it changing in the R direction or the theta direction? It looks like it's changing in the R direction based on my picture. So thankfully, I have, how is it changing in space crossed into the velocity components? What if they were the same? So it was changing in R and the flow was in R. It'd be 0, because that's what the cross product means. It means that you need to start with one, point towards the other, and this gives you the third direction. If at any time they're aligned along the same direction, you get 0. Okay, so let's try this again. This one here is changing with respect to R of U of theta. So is the vorticity here present? Yeah. This is non-zero. This is non-zero. And when they cross product each other, I go R, U, and the vorticity is out of the right? Now, this is a simplified assumption. Let's imagine that the water really can escape. Then as it goes around, there is in fact some UR, right? And there's changes in U theta, because now as it goes in, it speeds up faster. Then the vorticity would be even more intense. And so while for this specific example, we might get the same vorticity everywhere, depending on how the velocity flow looks. For a real sink that's really trading, you have vorticity that's actually moving throughout the fluid. Does that concept make sense? When I say vorticity can move?
What would it be if it wasn't?
Excuse me?
I said, what would it be if it wasn't moving? That wouldn't be.
So let me ask you this, okay? If I do something like this, right, and we don't let it come in at all, just going around. And let's say I draw U of theta in such a way that it changes radially so that we have the same omega everywhere. Right? Then it's not moving with the flow. It's the same everywhere, the flow. It's steady. Right? But what I'm saying is sometimes vorticity doesn't have to be steady. It can change with the flow. And it can move with the flow. Now, why is that? That's perhaps not surprising. Because vorticity is not a real thing. It's a product of the velocity. You are thinking about how does the velocity change to create this idea of vorticity. Right? Vorticity is not a unique property of the fluid itself. It's a derived property that we create by looking at the changes in an innate property. We see? So as that innate property changes direction, changes the time, then of course the derived property must be able to change. Check on that. Next. Okay, so therefore, we can define something called vortex lines. Just like we can define streamlines. And they are tangent to the vorticity vector. So let's go back to our example here. We're going around this way. Where is the vortex line?
Tangent to this. Or
What is tangent mean?
it's 90 degrees.
Okay. When we say that the velocity of the streamlines are tangent to the flow, what does that mean? What is that? Are you showing me with your arms?
Like,
Instantaneously, right? Like at a specific location, like you may have the flow do this, but at every location, the velocity is tangent to the flow. Right? Well, it would be coming out of the board, right? Vorticity is coming out of the board. So just like streamlines follow the stream flow, vorticity lines, vortex lines follow the vorticity. Now here, you could think of it as a single line out of the origin. That's really boring. And in fact, that doesn't represent the fact that it changes everywhere. So it's really an imaginary network of lines coming out of the board. Okay. So that's the part that's tricky, right? Because you kind of have to fill in with your head, okay, maybe at this location here, I'm thinking about one vortex line out. This one here, one vortex line. Here, one vortex line. And where it's the same everywhere, it's quite boring. But where it gets interesting and useful is when you can think about them in terms of varying vortex lines. So you could have a sheet of the same vortex value. So let's say that the vorticity is in fact changing with radius. Maybe it's the most spinny spin in the middle and it changes as it goes out. Then you could imagine there's a big column here, large vortex lines. And as you move away, the vortex lines get smaller, telling you that your flow is spinning less. Right? And this is telling us something about the fluid flow. Is that helpful? Okay. Okay. So let's have a little fun. Let's take an inviscid fluid. What's the inviscid fluid again? No viscosity, very good. The Navier-Stokes equation, if it's inviscid, becomes the Euler equation. Do we remember the Euler equation? What?
so it's the one that was written right there.
Different Euler equation. Sorry. Right? It's the total derivative of the velocity times the density equals contributions from the body forces, from pressure forces. Right? You remember those pieces? And then normally with the Navier-Stokes equation, you have two more. You have the shearing forces, and you have the compressibility forces. But if it's inviscid, you don't have any of those. It's just those two contributions. Okay. So if we have these inviscid fluids, and those are fine to approximate with, they can really help us to understand some of the vortex dynamics. When we're thinking about very large systems, we can just like say, well, vorticity, you know, the motion of the fluid is more important than the viscosity on these scales. And I'll show you how we can do that later. So we can start with this in order to understand some of the approximations. Maybe we should try it. We want to try it? Do a couple things really quick. Does everyone have 441 Euler equation ready and able to shout at me? Look it up.
Or be. Or big piece. Negative. Yeah, the name of the upside down triangle.
Right now.
Great, yeah, Del, I was like, I wasn't sure if it was, Del. Pressure plus rho G.
Pretty good, right? Easy. So this is Euler's. When viscosity equals zero. Right, that's what I want you to remember. And we can solve a lot of fun math that way. If I. Oh, I wish I had my click. Okay, I encourage you to try this when you get home. Okay, take a clear cup. With some sort of fluid in it, okay, and spin it. What shape does the fluid make on the surface? Caves in. Okay, let's draw that. This is Trinity's claim. I never said this, just Trinity. Here's how it is at rest. What happens when it's not at rest? A triangle. This is what you claim. Not perfect like that. Okay, so let's be a little. Okay, what shape is it?
Like a U.
Like a U. Okay, so like this. Capital U. I'm trying to be difficult. Okay, wait, let's try this again. So. Some arbitrary task, okay? Okay, so let's try this. I'm gonna take Daniel's U. I'm gonna go. Daniel, is that okay?
Yeah.
Okay, maybe we like that one just a little bit more. Why?
It has something to do with the being faster.
Here.
That's because it's all being squished to the sides, so it's all being, that's like the empty spot that's being formed because everything's going to the sides because of the centripetal force of the spin.
Okay, so remember that centripetal and centrifugal forces we've learned nothing about.
Gotcha.
We haven't talked about how we deal with something in a rotating frame. The only thing I'm telling you is that you have some cup of coffee or you have some fluid and you spin it. You're thinking about things being flung out, right? And the question is from the perspective of the fluid, it doesn't know that it's rotating, the cup's rotating, right? So from the perspective of the cup, a water's flowing. So we need a physical interpretation regardless of whether we're in the reference frame of the rotating object, which you're right, would introduce centrifugal forces, and that of the cup, which just sees a rotating fluid go by. Now, let's do a little quick analysis here, okay? What is the vertical velocity? Where's my, oh, there it is. Okay. There's different directions, right? So, okay. I'm going to simplify this a little bit. Instead of doing X, Y, Z, like I just drew on the board, I'm going to do Z. That's fine. Z direction. I'm going to do R. Is it changing in the R hat direction? And the third one I'll do is azimuthal. Theta hat direction. Right? Because that seems more natural. Okay. So at the very center, how is the velocity of the fluid in R? Here, how is the velocity of the fluid in theta? Because when I stand at the North Pole, I rotate around in a circle. So maybe I'm making this is solid body rotation, but I move quite quickly. Whereas if I go to the equator, the fact that I'm farther from the central axis means I move faster, right? So my velocity is actually fastest where on the cup? The outside. Right, that's really counterintuitive because we were thinking back in the context of Bernoulli's that where the object flows the fastest, that it should have the lowest pressure, and therefore, right, maybe it sinks. But we can understand this with vorticity dynamics. Okay, so let's try this out. I'm going to take Euler's equation. I'm going to take the corrected R, theta, and Z. I'm going to write out a few simplifications right here. So let's imagine the thing's in steady state. Can we do that? Okay. Then I just have two terms. So I'm going to say something like this. I'm going to start over here. I'm going to say it's solid body rotation. I'm going to say U of R. Wait, hold on. Did I say this right? Yes. U of R is equal to 0. Let's say the whole fluid is rotating together. Is that okay? And let's say that U of theta is equal to omega R over 2. And omega is still the omega we know and love. Okay. That's the rotation of this body. So let's write this simplified. I'm actually going to get two equations. I'm going to get minus rho U theta squared over R equals minus del R of P, and 0 equals minus del Z of P minus rho G. So what am I trying to do here? Well, what I want to do is I see, some stuff. I see that the object's rotating, solid body rotation. It moves fastest as I get towards the edge of the cup. It moves the least at the very center. And I want to understand what shape the surface makes. So I can start with my velocities. I'm like, okay, that's good. I know what the pressure is. Let's imagine, or not, I know what the density is. Let's imagine that is some function of the fluid. Let's not going to let it change, have it be a constant of the fluid. G, let's put that for Earth. That's gravity. And now I really just don't know how the pressure exists. How does the pressure vary in this fluid that's moving? Like, that's the thing that I want to know. Okay, so we drop the DDT part and we have an advective term on the left. And we have gradients on the right. So you can see that this term is this term, the DDR. This is one component. And then this term is this term, the DDZ component. Right? Now I need to go direction by direction in order to get this to work. Right? So you'll notice here that there's a U theta, but there's no UR term because the UR term is, of course, 0. So we're looking at a number of different equations, but they are happening, right? Whenever I write the Navier-Stokes equation, it looks like one equation, but it's really secretly 3 equations for each of the different components of the velocity, right? Okay, so now I have 2 equations and I have 1 unknown. That's fucking great for me. I'm stoked, right? Okay, so let's try to figure this out. I know I said never to do this. Hate crime, but I'm going to do it anyway. We integrate, and we integrate this one here. Okay. And you get something like P of R and Z is equal to rho omega squared R squared over 8 plus F C. Why did my constant of integration include a C? So when I integrate this thing here, right, P, so this dr comes over, right? So this only has r's on it and this only has p. When I do the integral here of dr, I don't know that p is not also a function of z. But I don't have anything here that depends on it. If you have a function that may explicitly depend on other variables, you cannot ahead of time simply write this without a constant that may include other variables that were not named. So I noticed this in the last homework. Because, for example, if you take the derivative of something and you get 0, let's say you take the derivative of a bunch of stuff, and that equals 0, then whatever you took the derivative of, okay, is a constant, but may have variables that are not the ones you took the derivative of. Let me say that again. D del x of y equals 0 tells you what about y? Constant with respect to x. But it doesn't tell you anything about z. Right? So if I take this derivative with respect to x, then whatever's in here is a constant with respect to x only. So that means that y equals, y can be a function of y and z, but it's a constant. That's the only way to do some of these problems, right? You have to identify that. Yeah.
So does that relate to what you were talking about, the Poisson equation where time equals space? Or is that something else?
This is having to do, if you did the homework that has to do with the escaping atmosphere, there is a section where you have something like DDR of something that has a lot of R's in it, and yet it equals 0. That seems impossible, right? It's only not possible if the integrand, or the thing that you're taking the derivative of here is constant with respect to r, with respect to x, wherever you take the derivative. So here you start with something that's rho omega squared r squared. That's the part that you just integrated perfectly, but you gotta count that there might be another term that you're missing. And so you do it again. You do it here for the z1. Okay. And check this out. What is the z1 be? P of z r. Anyone do that in their head? Come on, folks, you can do that in your head. Let me write it for you better. This is a constant. This is a constant.
PG.
PGZ, very good, thank you, but it's rho GZ, but that's okay. Rho GZ is correct. Notice there's no R's in there. As was possible here. So similarly, I need to add. H, okay. H of R. See how that's okay? Who's lost?
Also, why you did only Z? You don't know if pressure's working at Z or theta. So why do you only consider Z? Like plus Z.
Well, I know, so
Also maybe.
which one? No, the negative. Right? Oh, sorry, you're right. I've only moved one over. Good job. Your point was, why is there no function of theta?
You don't know. How come you only-
Yeah, you could put that. You could put it f of z comma theta. That's perfectly okay. I just didn't do that because I know better. Okay, sorry. Yeah, I know that's cheating, but that's okay. So now you look at this one and you look at this one, and you say, hey, those are good, right? So maybe this thing here is my f of z, and maybe this thing here is my h of r. So let's write this down. P of r comma z is, let's write the first term, that's rho omega squared, r squared over 8 minus rho g z. Am I missing? Why an initial pressure? Where is that in my equations?
So like, size to move itself, there's an initial pressure.
What do you mean?
Well, and I'm saying inside of like. The actual example itself, there's a pressure inside of it. Like that's the initial pressure. Inside take it from there's pressure inside there.
Okay. You're almost there. You're like 97.9% of the way there. The only thing that I would change there is thinking about how you have this intuition, right? You're saying the cup, when it's not moving, has pressure inside it. Good, that's right. That means that along the surface, at the boundary conditions, whether it's at the top, where you set x equal to 0, I need my equation to be non-zero. Right? So for your example, you say, okay, let's take the pressure at the very bottom. Let's call that z equals 0. I need the pressure to be non-zero. Right? And right now, what does it look like? I put z equals 0, and I put r equals 0, and it's not spinning. The whole thing is 0. So there's your like constant of integration. Now it comes from both of these, but it requires, again, the boundary conditions. You've got to plug in the boundary conditions to know what that answer is. Because you don't know if it's plus P naught or minus P naught. Now it is plus P naught here, but we can think about moving it to the other side, and we can think about changes from the norm. So these would be changes from the normal. Right? C'est bon? So what's the shape of this object? What's the height of this moving object?
You go from the bottom of the glass to the beginning of that little U dip, or to the top of the, where the water reaches. To the height.
Well, height, Z is just anywhere in the glass, right?
So that's the answer, right?
What do you mean?
The height is everywhere in the glass, or.
No, but I wanna know the boundary, what does the boundary look like?
Oh, we're solving for Z?
Yeah. Tell me what Z is. You can write it down, won't take too long. It's right.
Divide by. Minus. The PRZ. Minus the compression. Divide by. Oh,
Good. What does that say? What am I looking at? That's correct. These are parabolas. R squared. Z is a function of R squared. Right? So if I think about Z, the height of the fluid, it goes up. And that means I can draw little lines. This. And as long as these are parabolas, these are lines of constant pressure going down into the. Weird, right? Okay, so I gave you one homework assignment. Now you get a second homework assignment. This is not really homework, but you will want to do this. I want you to solve the tea leaf paradox. And this does not mean look up the answer to the tea leaf paradox. But you go home, put some tea leaves, or they don't have to be tea leaves, they can be like ground up pieces of grass. I don't give a shit. Okay, spin up the tea, and let it come to a rest. Where do you expect the tea leaves to end up? What are you on top? Okay, let's imagine they sink down.
Center.
Okay, there's two opposite parties. They're both LA caps, so I don't know what. Okay, so Daniel said, you said in the center,
Yeah, it's just like bunched up in the bottom.
you said thrown against the walls.
Thing like based on like what we have done in like today, that the fluid like, goes to the side, like centrifugal forces like make the stuff go to this walls.
Yeah, that seems pretty reasonable, right? So if Daniel was right, you'd be surprised.
Based on today, yeah.
Yeah, it seems right, right? It seems like, right? Let's try. Find out what happens. Okay. Okay. This takes us to, wow, really not moving fast today. Okay, my bad. But you're getting it?
I have a question, so we were talking about the vortex lines earlier. In this case, are the vortex lines pointing straight down into the bottom of the cup?
So that's a good question. Is there UZ? Are there vortex lines? little tricky, right? I'll let you do the vorticity on this. Okay. It's a solid body rotation.
Sorry, I know you've already explained this, but I've never wondered why the P naught is plus. Or not in this one.
Here,
Yeah,
it's chosen that way so that when I put R equals 0 and Z equals 0, I get a positive value. It's a convention. It could be negative if I wanted it to, but I have to say that the pressures were negative. Okay, so let's really quickly do Kelvin's theorem. So, who is taking Enon? Who is taking Enon? Okay. So, you're familiar with the idea of fields. These are not places to play frisbee. These are not places to play baseball. These are mathematical constructs of something that permeates all of space. Right? So we are going to use them as mathematical constructs, and we're going to take advantage of the mathematical formalism that fields have given us in order to construct information about fluids, stuff that we can use in order to solve problems. Okay? Electromagnetism is an analogous analogies field theory. Field theory just means that we treat things like having vector fields. They are defined everywhere in space, and they must be everywhere continuous. Okay? Oh, look at this one. It's a long sentence. In an inviscid barotropic flow with conservative body forces, the circulation around a closed curve moving with the fluid remains constant with time. What did I say? Flow. No viscosity, good. That's isobaric. Barotropic means pressure. Go ahead.
I was gonna say the one with temperature, but
The one without temperature.
there you go.
Barotropic, baro, your instinct there being barometer, right, which has to do with pressure. For barotropic means only having the pressure only has to do with the density, not to do with the temperature. Flow with conservative body forces, what are these? What? Not exactly. Conservative just means time reversal symmetry is good. So for example, if I throw a ball and I play that backwards, it looks the same in both directions. That means that I'm not losing any energy with those body forces. Okay? The circulation, now the circulation is something we haven't defined yet, but this is a stream property around a closed curve, so some closed curve, like here. Okay? Moving with the fluid remains constant in time. So as this property of the it's called the circulation, as it grows or expands, as it moves in the fluid, the total value of circulation must stay the same. This is going to help us solve some problems. Okay. So what is circulation? Go back one step here. I haven't found it right. We're going to compute the circulation. We basically just have a statement that's as simple as this. ddt of this thing. Okay, you wanted some new symbols? Get some new symbols. This is called circulation. And this is Kelvin's first theorem. And you may recognize Kelvin. What Kelvin is? Degrees Kelvin. Same dude. This work on physics 200 years ago, you get your name on everything. Huh? This is basically gonna tell us a couple different things when we're thinking about vorticity, that vortex lines, they move with the fluid. Now, that's maybe not so surprising. So as the fluid is advected, as velocity goes from point A to point B, it drags along with it vortex lines. Second is that circulation is constant along its length. Circulation is really just a measure of the vorticity. So what we're saying here is the strength of the vorticity in some closed area is going to be the same. What I mean by that is essentially what I'm going to do is I'm going to use my hands like this. Okay, and let's say I'm holding on to like 100 vortex lines. That's how much. Okay, when you draw something in E&M and you have lines coming away from your charge, right? If they're very close to one another, that means what about the field strength? It's strong. So when we draw the field, the density of field lines tells us about the strength. If I enclose a lot of vortex lines and then I squeeze my hands down, what happens to the vorticity? Has to go up. Okay, this is going to be a tool for us to use. This idea of this thing called circulation, which I don't have time to like write out mathematically, but we will on Wednesday, is going to be a measure of the vorticity field strength, so to speak. And it's going to be conserved along the length of a vortex tube. Okay, so as we move through a vortex tube, as the shape contracts or expands, this is going to speed up or slow down the vorticity, so to speak. Speed up is not really the right word, but you know, spin up maybe or spin down might be the better way to say it. And tubes don't end. Tubes have no start and no beginning. No start and no end, no beginning and no finale, right? They go on forever. And the circulation has to be constant in time. And that's the only part that's a little tricky. Okay, so we're going to solve some versions of this equation using Kelvin and Helmholtz's theorem so that we can use something like the circulation and we can get a steady state solution to fluids very quickly by solving the vorticity instead of solving each component of the velocity. Okay. Okay, questions, comments, concerns? Okay, so the next thing that we're going to do on Wednesday, we're going to go into this in a little bit more detail, and then we're going to take a box of fluid. We're going to take the very top plate, let's say that I can move that, and we're going to run a conveyor belt across the top. And we're just going to drag the very top layer of fluid. And I want you to think in your head what will happen. Sketch it out, right? And then we're going to come up with the mathematics to show whether or not that's true. Okay. Okay.